Okay, so on the back of the sheet that I just gave you, so generally, what is the sampling distribution? So this is what I was just making the connection of between last night's homework and like where I wanted you to make it, and what I did at the end were just switch things to proportions. So in general, and this is like for you to understand, not for you to get a literal definition. I'll give you a little definition on the next slide. So right here is we are attempting one, but this is an approximation. So we're making it, so we're making the graph. What do each one of those dots represent? A what? An outcome from a sample. So a sampling distribution is a graph of all outcomes from which samples if I were making the true sampling distribution. From all possible samples of, I'm going to say that scenario. So this is like very generic. So I made a graph and it's dots. Each dot represents a sample and each dot is a statistic. So in our example that we were doing on the board, each one of those dots was a what specific type of statistic? I don't know if you can see it. The bottom says 0 to 1, 0.5 is in the middle. So those are all what? You should not be overthinking this. This should be a really easy answer. Those are proportions. So those are p-hats. I could do it with x bars. I could do it with s. I could do it with anything. Those are just dots from each of the sample statistics. So that is generally what a sampling distribution is. Now I could talk about it with proportions. I could talk about it with samples or means. I could talk about standard deviations. Technically, I could talk about like medians. Most often, and the ones we're going to deal with are proportions and means. And we're only going to do proportions today. So this is like your sentence that I would expect to be on your test of interpreting the sampling distribution for a proportion. So it is a distribution of all values and that extra all is kind of, it technically doesn't need to be there, but I thought it makes more sense that you'll put it there. The values of proportions and I'm going to write it specific to our scenario. So what was it that we were doing? What was our trial? Well, each one of those dots represents what? When I did what? 20 coin flips. So it's the proportion of coin flips that did what? And so that one's an approximation, but the actual sampling distribution would be from all possible of what? And part of it you said, and I just didn't write yet. What were we doing? How many? So that is your like fill in the blank thing when we're dealing with proportion. Now, if I switch to doing it with means, not much is going to change there. It would be the mean instead of proportion. I'm going to see if I can get back in that Google Meet because it looks like the internet's back up. Okay. So the big point that I've made so far in the last couple days is the fact that it is all possible samples. The part that I haven't made a big point about yet is it is specific to the number of samples that we did. So like if I had a dot, if I flipped a coin 50 times, that dot would not go on that graph because it has something completely different. Even though I'm still flipping a coin, even though I'm dealing with counting weighting on heads, these are only ones that's 20 of them because everything would change if I changed my sample size. So now this chapter, a couple years, 2 years ago, 3 years ago, I started something called quick quizzes, which would be like once or twice a week, and they would be about 2 minutes, and it would be something like write the sentence or fill in these symbols. Last year we got them started, and then COVID happened, so we couldn't do them. This year it might be tough because so many people in and out with the 75% thing, so I don't know if I'll do them this year or not. This one I will probably do though. So at some point, either later in this week or next week, I'm going to give you a quiz where I hand you a piece of paper and it's going to look something like the bottom half of this sheet and you just write what each one is. So like you need to know this right now. So what is, and I talked about this before, that type this looks funny. So we call that one mu. What does mu stand for? What kind of mean? Mean of the what? Sample or population? This next one is sigma. Again, sometimes type looks a little bit funny. What does sigma stand for? Of the what does P stand for? Of the population, because hat is sample. What is X bar? What is lowercase s? What is P hat? I was very surprised the first year I started doing these. If you don't know what those symbols mean, you can't really do a problem. And so I thought I was doing something to like give everybody an extra grade, and about half the class knew these. So you should know these already. You can't really do a problem without them. So at the very least, know what they are. What is lowercase n? Number of trials or size, whatever. So what's the difference between lowercase and uppercase? And I just started talking about this like yesterday or 2 days ago. One of them's talking about the what? So this one is the sample size. And sometimes we say trials. That's the same thing. But I write it this way because it's easy to write it as population size and sample size. Number of trials in the sample and number of trials in this population still is technically fine. All right, so you got to know these. Now, typically, the ones that are Greek letters are going to be about the population, even though on this page, these two are not. But usually when we deal with Greek letters, they're about the population. What do we call them if they're a number about the population? It's from this chapter. Parameter, and what's it called if it's about the sample? Statistics, so make sure you remember that. So this is a connection, you don't need to write this. So we just went over what the different symbols are, but sometimes in the past, and we haven't made a big deal about this yet, like sometimes I write mu of x, or like mu of y, or same like with subscripts. So what does that mean when I put a subscript letter there? It's of that sample, or of that group. If I define let A equal this, and I find mu of, it's what I'm finding the mean of, the group or distribution over them finding it of. So today, we are going to find, and you don't need to write this, mu of p hat and sigma of p hat. So this means the mean of the sampling distribution of p hat. This means the standard deviation of the sampling distribution of p hat. So subscript x is what we usually do because we just have one data set. This means of the entire sampling distribution of that. So eventually we're going to move into that, which means the mean of the sampling distribution of x bar, standard deviation of sampling distribution of x bar, when we're dealing with means instead of proportions. All right, still on the back, but maybe if you use the left side, now write on the right side or something. So like kind of separate from what we just did, but you don't need a whole lot. It's the same stuff that's on the back, or on part of this is on the front anyway. So for sampling distribution of p hat, which I always call it sampling distribution of p hat, but it is the sampling distribution of the sample proportions, because p hat means sample proportion. So first thing I want to talk about, I know you're writing, is where the mean of that sampling distribution is going to be. So let's talk about our two examples, our homework example and our class problem from yesterday. In our coin flip example, or in our homework problem with the 3, where's the mean there? Where's the middle? 1.5. Why? Because that's the mean, right? We flip a coin 3 times. Flip it 3 times, probability 0.5. That gives me 1.5. In our example from yesterday's class, which I've got up here on the board, where is the center of that? And I know you can't really see it, but you probably don't have to see it to know where the center of that is. Where's the center of that going to be? Flip a coin 20 times. What do we think the middle of the proportion of number of heads is going to be? At 10 or half, if I know proportions. So why is it half? What is 0.5? So like you would answer this problem if I wasn't asking you this question, and don't write this. You would write what here? 2 days ago, 5 days ago. If I'm flipping a coin, what is 0.5? No, symbol, letter. So the proportion of my population is 0.5. It just so happens that the center of the mean of my distribution of p hat ends up being the same thing. Does that make sense? So if I take a sample and then take a whole bunch of them, So let's go back to the GPA problem we were talking about. If I want GPA of all JLMAN seniors, and I take a sample of 25 of them, some are going to be above, some are going to be below. But if I keep taking samples, the center of my samples should be about the center of my population. If it is what? Unbiased. So that's where this is. If this is right, if we took it from all of them, we should get the exact center. So this part, I do want you to write, just that part. That's just right.
So is that specific to what the plan was?
That one is, yes. I guess if you don't, I guess I probably should have just written number there. Or if you leave it as 0.5, just do like coin flips. All right, so standard deviation. What is my symbol going to be here for the center of this graph of all of our dots? So this was mu of p hat. This one is going to be what? And so this is actually on the front of your notes, but I'm writing on the back together on purpose. So the standard deviation of the sampling distribution is, or a p hat is, so without going through like the deriving the equation part, because I've done that before and I just don't think it's helpful. The p in the 1 minus p is kind of like when we found the standard deviation of a what? Like the square root and then dealing with p and 1 minus p, that's kind of like dealing with the standard deviation when we found it for a what? It's kind of like geometric or binomial, that part is in there. So the part that we haven't ever dealt with before with the standard deviation is what? Your n. So when we are taking samples, so each dot up there is a statistic from a sample. Does it matter how big our sample was? So let's say I'm selecting seniors, and I just so happen to get about 4 seniors that are about in the middle, and I get one who has like a 0.2. If I only took a sample of 5, is that one person going to affect a lot? Yes. If I took a sample of 20, and that one person still gets in there, is that person going to have as much of an effect? So is the sample size going to matter with your standard deviation? Yes, and that's why it's in here. So what do you think is going to happen to your standard deviation as your sample size gets bigger? It's going to decrease. So as your sample size gets bigger, that outlier has less effect, so it's going to decrease. I need you to write that. That standard deviation only applies if 10% condition. Which we don't want to write it. Tell me in words what just this little piece right here means. What is this talking about? My population size needs to be. So if I took a sample of over here, I'm flipping coins. And my sample size was what? 20. 20 times 10 is 200. Is it possible that I can flip the coin more than 200 times? Yes, so we're good. If we are dealing with the seniors scenario, y'all probably have a better guess than I do about how many seniors there are. 500-ish, okay, we'll go with that. So let's say that 500 is the number of seniors there are. How big could my sample be? Less than or equal to 50, algebra. To make that work. You with me? The y part in there is something with the multinomial coefficient with the combination as n goes to infinity, then the coefficient turns to 1. Y'all don't need to know that part. You need to know this. And basically the reason why is if we take too much of the sample and only leave out like a piece, so like let's say we've got that one major outlier of somebody who has like a 0, and we only have one of them, and I take a sample size that's like 90% of the senior class and I leave out that one, then my estimate's going to be really far off because I left just that one out. Whereas if I make the adjustment knowing that I have a small sample size, because this is the adjustment for knowing that I have a small sample size, then that adjustment's going to make up for itself. That's the part that you need to know. You don't need to know like the depth of the equation stuff behind it. So this all applies for a sampling distribution of p hat. Looking at the graph, and it's not 100% done, what can you tell me about the shape of a graph of the sampling distribution of p hat? Pretty bell shaped. Symmetrical. Where is it centered? Which is the what? Centered at the mean. Or which is centered at actually the parameter. So that's the majority of what we're going to get through today. So go ahead and flip it back to the front. Now, what we just went through is most of what's on the left side. I just don't like the way that it's written. Oh, I do want to write one more thing on the back, but I'm going to go through what's on here first. So the beginning through the bullet point says, choose a simple random sample of size n from a large population with population proportion p having some characteristic of interest. Let p hat be the proportion of the sample having that characteristic. So then it just talks through what we just said. The mean is this. The standard deviation is this. The standard deviation only applies when the population is 10 times larger than the sample. So I just like the way it's written, the way we did it, then written out in words like this. So when the sample size is large, sampling distribution of p hat is approximately normal. So this is the part that we need to add in. So underneath right here, I want you to write normal condition. We'll just write normal. And this is actually something that's different in different textbooks. And it's different with what level of statistics you're dealing with. But the general idea is that you have to have a reasonable number of successes and a reasonable number of failures. Saying it wouldn't apply, this would not apply to something that is like, what's something that's super unlikely? The likelihood of getting struck by lightning. Like the probability of getting struck by lightning is so tiny that if that were my success and not getting struck by lightning is my failures, then it wouldn't fit this distribution. We need to use something else. So our way of checking that is that, how do I figure out, no, I'm going to write this and then go backwards. That has to be greater than or equal to 10. So in general, what does n times p this is proportion of what? Whatever successes is. So our proportion of successes multiplied by our n. So this is like dealing with number of successes. So this is going to deal with what? If this is dealing with number of successes, this is going to deal with How can I figure that out using that same type of equation? The only thing I change is what? So right now it's technically not the number of failures, but it's like the theoretical number of successes and number of failures. So if both of those, then we can use normal approximation. And I get extremely picky right here for the first couple weeks. Did I say it is normal? No. I just said we can use a normal approximation. So it is close enough to where the numbers from the green sheet would be reasonable enough to use to estimate, not that it perfectly fits that curve exactly at every spot. And I will tell you, things start to get very, very repetitive at this point. And it's kind of up to you if you want to do well or not. And if you want to sit there and not pay attention to me like some of you are right now, then you're going to see a big difference quick. And those of you who are paying attention will think this is easy. All right, so example 1, Gallup poll is to the right side. Gallup poll once asked a random sample of 1,540 adults, do you happen to jog? Suppose that in fact 15% of all adults jog. Problem does not ask this, but what is our sample? The adults that were sampled. So the 1,540 adults that were sampled. What is our population? All adults, not all adults who jog. Where does the jog come in? That's our success that we're talking about. All right, so found the mean of standard deviation of the sampling distribution of p-hat. So tell me what to write in symbols.
What's the difference between just finding the mean and finding the mean of p-hat?
All right, so this is of all coin flips, like concept-wise. This would be all of my 20 coin flips. This is all of my 20 coin flips. This is the mean of all the dots of all the 20 coin flips. Does that make sense?
Yeah.
So this one is just talking about like a general population. This one is talking about I made all of, sorry, I need to keep pointing because people online. This is I'm making a dot for every single p-hat that would be in the distribution. Now where is the mean of the dots? So when we're talking about proportion, it ends up coming back to this same thing, basically because of what we just said. But all right, so this equals what? So it actually told us, suppose in fact 15% of all adults jog. So is that a parameter or a statistic? Parameter. So this is kind of a weird problem. It says we took a sample. It doesn't tell us what we got out of the sample, but it told us what the parameter was, which is kind of where we are in the notes right now. So now, what do I write for standard deviation? Equals what? So I'm just plugging my numbers in there. So I'm plugging in the 0.15. I'm plugging in 0.85 or 1 minus 0.15. And what is my n? And you get, let's do 4 decimals. And we don't want it, I think it's 0091, but I want somebody to double check me. I feel sure that y'all can plug that in the calculator. I'm not worried about even correct this. Alright, now, I should on my own at this point know that I could only use that if what? If the 10% condition applies. Now, this one actually asked it in B to make sure because this is the first time we're doing it. So I would kind of make a note. So like, if I give you a typical problem, I'm not always gonna ask you, explain why you could use that. I would expect you to know to say that because that you can only use it if you check. So 10% condition. And what is my 10% condition? Alright, so which number do I have, the capital or the lowercase? So 10 times 1540. Capital N is greater than or equal to, so 15,400. And I am going to write what that means. So we already talked about this. What was our population for this problem? All adults. Is that correct? So a lot of times when I do conditions like 10% and normal, I'll do a check beside of it. Like I wrote it, but I kind of have to check it. And we'll just write, there are at least 15,400, did say US adults or just adults? So I'm being as specific as the problem, including my population.
So if it was something like more specific than talking about all adults, if it was talking about like one of the airport problems.
Alright, so I know what your question's gonna be, so two scenarios here. One is going to be they give you the population size, or you would write right before there, that's it.
Okay.
So like we're gonna deal stuff with like a large, they'll say something like a large university has, and now technically you don't know what it means to be a large university, I'm not gonna expect you to say that, but if you just say assuming that means there are at least this at that large university, then that's how most of our questions are actually gonna be answered.
So we're not gonna have to like check and
No.
make sure that it applies. We just have to-
Like you basically say, I know this is what I'm supposed to be checking, I'm not going outside context, so yes. Now, if you were actually doing statistics outside of class, yes, but this is the extent that we need to get. Alright, check that you can use normal approximation. And so I always get in the habit of writing, see, I always write normal with a question mark because I'm checking to see if it is normal, which we'll end up putting all together, but it's just out of habit. And then I come back and usually check it or exit. So what am I checking here? And so now I'm just plugging in my numbers. So 1540 times what? I think I can get through this without switching just the next couple minutes. 0.15. I'm just going to tell you what this says. And then I kind of keep my work going underneath. So 1540 times 0.15 is what? $231. So that's supposed to say 231 is greater than or equal to 10, and I put a check. Now, I'm still going to write out my math here, but if I didn't have this, how would I figure out what this bottom number is going to be? Like, what's the other way I could do that? This is 231, so what's this? However much is left, so 1540 minus 231. It just kind of helps you check your mistakes a lot. So 1540 Supposed to be 1540 times 0.85. So it ends up giving us 1269. Is that right? No, because it's 40.
1,309.
So 1,309 is greater than or equal to 10. So we can use a normal approximation. I know you can't read this, but you do have to write, so we can use normal approximation. And without getting there today, you should know, what does it mean when I say we can use a normal approximation? We can use the green sheet. So what this is working towards is saying, okay, I know what the population looks like. So if I know what the population looks like, I'm going to take a sample, and does my sample look like it's reasonable or not? So what we're actually doing here is trying to figure out basically if I'm getting a sample that's a good one or not. So like if I were to, let's say I were doing one from AP Stat to try to get senior GPA, I would probably get numbers that turned out really bad when I did the normal approximation because that wouldn't make sense with our real distribution. And that's the part we're going to get into tomorrow.